Unit 1, Activity 3, Definition of Function. If we put money into a vending machine and select coffee, we have an expectation that we will receive a cup of coffee, isn't it? This simple transaction enables us to predict an outcome based on our actions. Imagine a machine where selecting coffee could deliver you either a cup of coffee or milk or soda, but you couldn't predict which. Most of us would avoid this kind of vending machine. In math, as in life, we desire relationships that are predictable. Previously in Activity 1 and Activity 2, we used tables, graphs, and equations to describe relationships between inputs and outputs, your x and y values. In this activity, we studied functions, which require that our relationships have the property that each input has a single and predictable output. I repeat, each input has a single and predictable output. And these are our learning outcomes for our communication. All of you will identify functions in a variety of everyday contexts and explain why the relationships are or are not functions. The other one is interpret function notation in context. And in multiple representations, you will identify, use, and evaluate functions in verbal descriptions, tables, graphs, and equations. And also, you will be able to find algebraic models for linear functions given a table or a graph. Let's start with a warm-up. I want you to pause this and try to solve the two problems. Okay, let's try this. Number 1, for the equation y equals 12 over x minus 5, what is or are the output values if the input is 3? So all you have to do is substitute 3 to x. So y equals 12 divided by 3 minus 5, and 12 divided by 3 is 4, and 4 minus 5, yes, y equals negative 1. Very good. The second problem, for the equation y squared equals x, what are the output values if the input is 4? So let's try to substitute 4 to x. Y squared is equal to 4. Now, how do we solve for y? How do we isolate y? What do we need to do to get rid of that squared? That's correct. Square root both sides. So when you get the square root of y squared is y, and square root of 4 is plus or minus 2. Why is that? Because, take note of this, 2 squared, 2 times 2 is 4. Also, negative 2 squared is negative 2 times negative 2 is also equal to 4. That's why we have two answers, positive and negative 2. Try the next problem. For the graph shown in figure 3, what is or the output value if the input is 5? I'll give you 10 seconds. Okay, input is 5, so meaning that is your x. When x is 5, the point on the graph is this. So that is 5, 1. So the output is 1. So we can say that when x is equal to 5, y is equal to 1. Let's do the same thing for the next problem. For the graph shown in figure 4, what are the output values if the input is 2? Pause this and try it again. Okay, again, input is 2. Let's look at your x value 2, and on the graph, you'll see that you have 2 points on the graph. That this point, this is 2, 3, and this point is 2, 5. So meaning you have 2 output values That is, when x is equal to 2, your y values are 3 and 5. Did you get the same thing? Very good. Next, let's start with our class discussion. I love apples so much that I buy and eat at least one apple every day. I have recorded the number of apples I purchased each day last week and the amount I paid each time. Input, that is the number of apples purchased, and output, the cost for the apples purchased. Let's say 2, it was $1.50. When I bought 3, it was $2. 1, $1 for $2.50. If I buy 2 apples tomorrow, how much do you think I will pay based on this? What do you think? Yes, you will see that with the number of apples, 2 apples, there are 2 possible answers, $1.50 and $1.75. How about change one of the numbers in the table of data above so every number of apples purchased has a single cost for the apples purchased? So what do we do here? So maybe we change this to $1.50 so that they are the same. After the correction in part B, the table now shows a function that is each of the input has a single output. Look at this. 1 apple it costs $1, 2 apples $1.50, 3 apples $2, and 4 apples $2.50. Does this table show a linear relationship? Remember to provide your calculations and justifications to your response. So let's try. So let's say if we want to try to get the slope of this, slope, remember, is rise over run, and that is the change in y over the change in x. So let's say, let's do that $1.50 minus $1 over 2 minus 1. $1.50 minus 1 is 50, 2 minus 0.50, 2 minus 1 is 1. So that is 0.5 or 1/2. Also, another way to do that based on from the table, you can get the change in y here. 150 minus $1 is 0.5. 2 minus 1 is 1. Let's try this. $2 minus 150 is also 0.5. This is also 1. How about this? 250 minus 2 is 0.5, and this is 1. So it shows that there is a linear relationship with a slope of 1/2. And if you want to find the equation of this line, remember y equals mx plus b. If we have our slope 1/2 or 0.5, how about let's use the first ordered pair, 1 and $1, 1 and 1. So if you use that, 1 equals 1/2 times 1 plus b, and that is 1/2 times 1 is 1/2 plus b. If you subtract 1/2 and 1/2, 1 minus 1/2 is equal to 1/2. So now we will be able to write our equation, y equals 1/2 x plus your y-intercept 1/2. Next one, let's discuss the definition of a function. That is a relationship in which each input is associated with one and only one output. Again, the input is associated with one and only one output. Variables in notation, often people use x as the input or the independent variable, but you can use any variable you want in solving problems. Instead of writing y as the output or the dependent variable, you write y equals f of x, and we say that y is a function of x. For example, we can write the equation y equals 5x plus 3 as f of x is equal to 5x plus 3. But be careful, in math, parentheses usually indicate multiplication, but here you see that f parentheses x, that does not mean f times x. Okay, it does not mean multiplication. And in this activity, you will practice working with this notation. Okay, refer back to the warm-up problems on page 49. The picture below here, 2 of those 4 problems showed relationships that were functions and 2 showed non-functions, which 2 of the 4 warm-up problems showed functions. So remember again our definition of function, that is a relationship in which each input is associated with one and only one output. Okay, so number 1, is this a function or not? Yes, this is a function. For every value of x, which is your input, you will have a value of y. And you will always have a one and only one output. How about number 2? Y squared is equal x. Based on our example, remember y squared is equal to 4, and when we solve this, we got y is equal to plus or minus 2. And here you have 2 values of y. So this is not a function. Number 3, look at the graph here. A parabola that opens downward. And as you can see here, for every input, there is exactly one output. And yes, this is a function. And how about number 4? For every value of x, which is an input, so let's say 2. And you will see here that you have 2 values of y. Let's say 6. You will see that you have 2 values of y here. You have more than one. So this is not a function. So the functions are number 1 and number 3. Next, determine if each of the following relationships are functions. Let's start with these 2 tables. I want you to pause and try this, A and B. Alright, letter A. You have the table of values x and y, and you can see here that every element in x is related to y. And also, we can say that no element in X based on the table has two or more relationship. How about letter B? You have the X values 1, 1, 2, 2, and 3, and the Y values 3, 4, 5, 6, and 7. So yes, it's not, because values of 1 and 2 are related to more than one value in Y. How about C and D? C inputs are student ID numbers, outputs are the student's phone number. So we know that every student has their own phone number. So yes, this is a function. Okay, letter C. Again, inputs are student ID numbers and outputs are the student's phone number. So we know every student has their own phone number. So yes, it is a function. Letter D, inputs are student ID numbers, outputs are the student's current height. So it's possible that students have the same height. Is that right? Is this a function or not? Think about it. And I'll let you think about this problem. Okay? How about these two? Two graphs determine if each of the following relationships are functions. The first one, every element in X is related to Y. So yes, this is a function. How about F? It's not, because let's say values of X, let's say this X here, you have more than one point, more than one value of Y. So remember, I can only have one output for a given input. So this is not a function. How about G, Y equals X cubed? It's a cubic function. So you try, when you substitute values of X, say 1 cubed is 1, 2 cubed is 8, 2 times 2 times 2, 3 cubed is 27, and so on and so forth. So yes, it is a function. H, plus or minus square root of X. You can say, let's see, if X is equal to 2, just like an example, our previous example, and here Y is square root of 2, or negative square root of 2. Same thing if, let's say, we have, if X is 4, square root of 4 is positive 2 and negative 2. So this is not a function. Next one, evaluating functions refer to finding an output value when an input value is given. You have f of x equal to 2x plus 3 and g of x equal to 12 over x. Let's substitute 4 to the x. 2 times 4 plus 3. 2 times 4 is 8 plus 3 is 11. How about g of 4? So that is 12 over 4 is equal to 3. Next one, g of negative 6. So 12 divided by negative 6 is equal to negative 2. And the last one, f of negative 3. 2 times negative 3 plus 3. 2 times negative 3 is negative 6 plus 3 is equal to negative 3. Next, identifying inputs and outputs in a word problem is more straightforward when functional language is used. Take note of these phrases. As a function of and in terms of, when used in word problems, always identify the output before the phrase and the input variable after the phrase. Example number 1, the population of Pittsburgh is a function of the number of years since 2005. Since we use the phrase as a function of here, meaning after the phrase that is your input, the number of years since 2005, and output is before the phrase as a function of y equals the population of Pittsburgh. Let's have another example here. The volume of a balloon in terms of the length of its radius. The phrase in terms of in this statement means after the phrase in terms of, that is your input, x, that is the length of the radius, and before in the phrase in terms of, that is your output, y equals the volume of the balloon. How about an example here? Letter A, the number of units a student is currently taking is a function of their student ID number. Clearly define the input and the output variables for this problem. Is this description actually a function? And remember to provide justifications to your responses. So the input is after the phrase as a function of, meaning that is a student ID number. And the output is before that phrase is the number of units a student is currently taking. Number of units Next question is this a function or not? Yes, it is a function. Let's say we can illustrate a table of values. A student with, let's say, 1 as a student number, and this student is taking, let's say, 5 units. Second student maybe maybe is taking 9 units, or the third student is taking 12 units. So yes, it is a function. How about letter B? Consider the relationship of a student's ID number in terms of the number of units the student is currently taking in terms of. So to write our input and output, so input is after the phrase, that is the number of units that the student is currently taking. and the output, which is your y, is before the phrase, which is the student ID number. Now, is this a function? So let's have an example here. So let's say you have x and y inputs and outputs. So let's say number of units, 9 units this semester, and it's possible that student 1 is taking 9 units, student 2 is also taking 9 units, or even student 3 is taking the same number of units. So meaning this is not a function. Last one. A relationship describes the height of a tree in terms of the number of days since it was planted as a 9-inch sapling. Clearly define the input and the output variables for this problem. In terms of, that's the phrase, so input is after the phrase in terms of, which is the number of days since it was planted as a 9-inch sapling. And the output, which is your y, before the phrase, that is the height of a tree in inches. Now, is this actually a function? What do you think? Yes, it is a function. So as the number of days increases, that is the same thing with the height. Right, that is activity 3. Thank you.